All right, hello. We are talking about angular momentum today. Weird emphasis because the symbol for angular momentum is an L. I don't know why. We're out of letters, so angular momentum is an L. Just like regular momentum, it's defined as how hard it is to stop an object, specifically in this case, how hard it is to stop an object from spinning. Okay, we are starting with our basic point mass example. Okay, and so we can determine the angular momentum of a point mass by doing R cross P. So this is a cross product. We'll talk a little bit more about what that means mathematically here in just a couple minutes. But I wanted to briefly mention like the directionality of this is kind of strange. In order to notate rotation in like your Cartesian XYZ axis, like you do have to use all three directions because like clockwise and counterclockwise, you can't really, you could represent that in X and Y, but we notate it in the Z direction usually. So like this counterclockwise rotation that we have here, we could also say that it's in, I guess depending on how you look at this, it would be in like the positive Z direction. And so I use right-hand rule in order to establish this. And don't fret if you don't understand right-hand rule right now, because we're going to hit it much harder when we get to electricity. But the idea is I take my right hand and I hold it flat, like I'm going to give like a high five, right? I kind of put my wrist at R equals 0, and I let my fingers extend along the radius. Okay, so then I'm going to adjust like the direction that my hand faces so that the velocity is in the direction of my palm, or the directions, like if you were to curve your fingers, right, it would be in that direction. Okay, and then the direction of your thumb, right, is going to be in your third direction, your X direction, your Y direction, so it'll be in your Z direction. And that is, weirdly enough, the direction of your angular momentum in this case. So again, don't fret too much about that. Hopefully this little vector diagram will make sense soon. Okay. Oops, did not mean to doodle there. So let's just do a very basic example. The angular momentum of a point mass. So for a point mass, as long as the axis of rotation is like outside of the body, you can treat it as a point mass. So there might be some other terms that you want to add, but in general, right, if something is orbiting something else, treat it as a point mass. So if we were to consider the Earth going around the sun, right, I need the mass of the Earth. I need the distance between the Earth and the sun, which is 1 AU. And, well, I had to convert it into SI units. No being lazy here. So I converted it. And then for my velocity, I had to think about it for about 6 seconds. It takes 1 year, right, for the Earth to complete one complete rotation around the sun. And so if velocity is 2 pi r over t, well, let me convert that year into seconds. You can see my dimensional analysis there. And then we start plugging in. Okay, so it's r times p, which is r times m times v, which is 2 pi r over t. I paused here because I wanted to point out, like, you see the mr squared, right? You know that is the moment of inertia of a point mass. Okay, you also see 2 pi over t. That's actually your angular velocity, right? We cover 2 pi radians in one complete rotation in one period. So you can kind of see where we're getting at, that it's omega times I, right, is what we are looking at here. So hold that thought as we crunch some numbers. Crunch, crunch, crunch. I have utmost faith in your calculator skills. You should get 2.67 times 10 to the 40th kilogram meters squared per second. No cute units here. It's pretty much the regular momentum units times an extra distance unit of meters, since it's r times p. Okay, so that is angular momentum of a point mass. Okay. One of the strange things that you can also do is you can calculate the angular momentum of a translating object. You just need to establish a reference point. And sometimes the reference point is obvious. It's going to be like about some pivot point that's, very clear in the question. Or sometimes they will give you like an arbitrary reference point to work from. And so let's consider in this scenario, we've got a 2 kilogram object traveling at 3 meters per second downwards on like a Cartesian plane. And we want to determine the angular momentum about the origin. Okay, so if angular momentum is r cross p, right, so we should draw a radius, which is going to start from the origin and go to the dot, right, the object. So a little bit more about the cross product, which we've touched on a couple times before. Your cross product is a way of multiplying vectors where you only multiply the perpendicular components together and you get a vector as a result, right? That's why angular momentum is a vector. You multiply two vectors together. And if you do a dot product, multiplying the parallel components, you get a scalar, like with energy. But in this case, torque and angular momentum, they are cross products. We do get vectors that can be determined, their directions can be determined through the right-hand rule. So what we need to do is we need to split r into components. You can see I've done rx and ry. So the part of the radius that is perpendicular to the velocity is rx. Okay, so this one just happened to work out. It was much easier to split the radius into components than to split the velocity into components, but both ways work just fine. Sorry, let me pause for just a moment. Okay, if I pick a different, like, arbitrary reference point, like 2, 0, right? In that case, there is no radius that is perpendicular to the velocity. Like, you are, like, right on the spot, right? So no angular momentum is going to be measured relative to that reference point, okay? So, like I said, it'll be really obvious in the question. Like, if there is, like, a obvious point of rotation, you'll probably use that. But sometimes you'll be given like an arbitrary one to work around. Okay, so those are the two kind of special cases. Much more generically, much more typically, right? We've been working with our different like uniform shapes, the ones that we have moments of inertia for. We can calculate the angular momentum of those objects just by doing I times omega, right? It's the rotational equivalent to m times v. Okay, so we can go back to considering the Earth, right? It's roughly a solid sphere, rotating on its own axis this time, right? Which is going to take 1 day to make one complete rotation on its own axis. So you can see that's my angular velocity, a dimensional analysis there to get the Earth's angular speed of 7.27 times 10 to the negative fifth. All right, we math, we crunch our numbers. Yeah, don't forget to square what you need to square. I almost forgot to square my radius there. It was close. So, but I'm pretty sure that we should get 7.07 times 10 to the 33rd as our angular momentum. So, calculating angular momentum in isolation is all well and good, but we would actually like to apply it to some physics, specifically the idea of conservation of angular momentum. So just like with regular momentum, this is going to be valid if your net external forces or torques, right, are equal to 0. So torques in this case. One of the unique things about conservation of angular momentum with like rotation is that you can actually do it on a single object, right? Our classic example, as you can see here, is for our ice skater. Our ice skater, towards the end of their performance, they spin, right? And they usually tuck in their arms and legs and they spin much, much faster. Right, that is exactly, what conservation of angular momentum should be used for. In this hypothetical example, we see that our ice skater reduces his moment of inertia by 1/2, like a factor of 1/2. And so his final angular speed is going to increase by a factor of 2, right? Those two quantities are inversely related. Something interesting to note, right? Your starting angular momentum and your ending angular momentum are the same, right, since there were no external torques. However, your starting kinetic energy and your ending kinetic energy are not the same. In fact, your ending kinetic energy is higher, right? We saw that omega increased, right? So you've got, I omega is equal to I omega, right? And 1/2 I omega squared, and the final 1/2 I omega squared, because that omega is squared, right? Your final kinetic energy is going to be bigger than your initial. And so what that implies then is that the act of pulling in your arms and legs, you do positive work, I guess, on yourself, right, on your arms and legs, in order to actually pull them in. It makes sense, right? The force is with the motion of your arms and legs. That is by definition positive work. So that checks out, like, from a logical standpoint. Okay. More traditionally, with conservation of angular momentum, of course, is a collision. Usually this is going to be like a child running at a merry-go-round in some form or fashion. So just keeping this super duper generic, a child runs at a disc shaped merry-go-round with some speed v. The merry-go-round, we can assume, starts at rest. You can see there on the left-hand side, MVR. That is the angular momentum for a point mass that we derived on the first page. Okay. Then you can see on the right-hand side there, right, they stick together. We are treating this as a completely inelastic collision. Okay, both the child and the merry-go-round should be rotating at the same angular speed, assuming, the child is hanging on and not actively, walking forwards or backwards on the merry-go-round as it spins. Okay, so we lump that together. It's like your total moment of inertia times the angular velocity. We rearrange. Now, I did want to point this out here. Since the child attached himself at the very edge, right, I was able to cancel out one of the R's in this expression. But if the child did not hit at the edge, so say that he, approached the merry-go-round closer to the center rather than the edge, then that R is going to be different, right? And then you won't get such a nice, neat cancellation there. Okay, so just something to keep in mind. Yeah, let's keep going. So we talked about conservation of angular momentum, and then we should talk about the impulse momentum theorem, aka Newton's second law as he originally wrote it. Remember that Newton originally said that a force is defined as the rate of change of momentum. So same idea here. A torque can be defined as the rate of change of angular velocity. And then, are very obvious, if the torque is with the velocity, then you will speed up and your angular momentum will increase. If the torque's against the velocity, you'll slow down, the angular momentum will decrease. And then, this is the one that everyone hates, if the torque is perpendicular to the angular velocity, then that means that the direction of the angular velocity will change, which is the same verbiage that we used to describe uniform circular motion way back a couple months ago. Okay, so you like rotational motion so much that we put circular motion in your rotational motion. You'll probably only see conceptual questions on this. At least I hope that you'll only see conceptual questions on this. But your quasi-familiar example is going to be like a gyroscope or a spinning top. Okay, so let's consider, my art skills aren't great, right? But consider there's this top. We give it a spin counterclockwise. All right, and so according to right-hand rule, that is going to be that kind of up and to the right direction is my angular velocity and my angular momentum. Okay, so when your top starts, winding down, right, it starts to lean a little bit, all right, and so the moment that it's no longer perfectly upright, there will actually be a gravitational torque that is involved. And so you can right-hand rule that. And so the torque is actually going to be going into the page. Okay. The way that we notate that symbolically is with an X, usually an X with a circle around it. Okay. Just for your information to indicate that something is going out of the page, that's going to be a dot, just like a dot, usually with a circle around it, but not always. And you can think about archery, you're shooting an arrow and you see the feathers going away from you, or someone is shooting arrows at you and you see the arrow head at you. So, that was a little chunk of text there. So this torque due to gravity makes the angular velocity go more into the page. So this top, as it spins counterclockwise, it's also going to have an even greater counterclockwise motion. So you've all probably seen this, right? If you spin a top, right, as it winds down, it starts making the little loops and loops and loops. And it gets wobblier and wobblier as it goes. And so this is how you determine the direction of the wobble. Okay. And so that is hopefully all you have to do with precession. You just have to know what it's called, and you have to know kind of conceptually what to do with right-hand rule. I would recommend watching the Veritasium video on gyroscopic motion if you're looking for more detail onto that, because he is great. So